Hello, Algebra 1 class. This lesson, lesson unit 3.8, is about using the correlation coefficient. This value, the correlation coefficient, we learned first about it in lesson 7, and this is a continuation of that lesson. The learning targets are: I can describe the strength of a relationship between two variables, and I can use technology to find the correlation coefficient and explain what the value tells me about a linear model in everyday language. In this warm-up, you want to match the variables. So number one, you have an x variable and a y variable with which graph, A, B, C, or D, or which scatter plot, it would best fit. And likewise, number two, number three, and number four. Go ahead and pause the video and do that now. All right, here are your answers. The first one, A, is the most linear relationship we have, and that is the x variable being measured student height in feet and the y variable being measured student height in inches. So ideally, this is just a conversion, and this better be a linear relationship. The B graph is the second one, and we have on the x-axis the average number of free throws, and on the y-axis the basketball team score per game. You would think more free throws gives you an average score, but it's not necessarily a direct linear correlation. C is the one that's the most scattered, and here the x variable is the daily low temp in Celsius for Denver, Colorado, so the temperature, and the y-axis is the number of boxes in stock at cereal in Miami, Florida. So they're not even in the same city. And what do boxes of cereal have to do with how hot or cold out it is? And that leaves our last one, D, which is the fourth set of variables. And this is your average number of minutes spent in a waiting room and the hospital satisfaction rating. Ideally, your rating goes down the longer you have to wait. Or you could say it, the longer you have to wait, the less satisfied you would be with the hospital. And you can see this is a decreasing relationship. What I want to do with this slide here is just to explain how to use Desmos to find a correlation coefficient. This data that's plotted here and that is in this table is your data from the scatter plot A from the warm-up. It's your student height in feet and in inches. And if you open the file that I gave you to go with this, you can go ahead and open Desmos and enter the same data. You should get a scatter plot here. So enter your scatter plot first. That's in this bucket here. And that's choosing plus and then table, the plus sign being up here. Then once you have the scatter plot drawn, go ahead and enter a new plus sign, and you're going to choose f of x, or function. And what you need to type in is this, y1, and the tilde mark, which looks like this, you get by choosing the keyboard and then click the ABC button, and then you can choose the tilde, and then you type in the M, X, and you don't do a subscript one, you just type X, capital 1 or large 1, and it will make it a subscript, and then plus B. And when it does that, it immediately returns the slope and y-intercept of the line of best fit. So you can write this equation, y equals 12.05x, I rounded to the nearest hundredths, minus 0.23. So that you can see is a positive slope, and we have our linear relationship going up, and our y-intercept is just below 0. The other thing it gives you right away is your correlation coefficient. So there's actually an r squared value and the r value. We're looking at the r value right there, and it gives it to you automatically. So in this case, r is 0.9992. That is so close to 1. 1, it's positive because this is an increasing relationship, but also it's so close to 1, which means it's a very good correlation between the height in inches and the height in feet. This slide just helps give you a summary of the different kinds of relationships that you will see based upon your R values. So you can have a negative relationship. In this case, your R is negative because the slope is negative. It's going down, it's decreasing. And it is a very good fit. So this is very close to -1. The next one is a line going up. And so this R will be positive because it's an increasing relationship. And it's also all these variables are very close to the line, all these data points. So your residual plot will be very close to 0. And so this R value is close to +1. If we look further, we have the difference between a strong relationship and a weak relationship. So both of these R values are positive, but you can see that the strong relationship, they're very close to the line, and the weak relationship, they're very scattered, although still increasing. In this case, your R is very close to 1, and here the R is closer to 0, but still positive. In this activity, you are going to be using Desmos to create a scatter plot, calculate a line of best fit, and look at the model equation as well as the correlation coefficient. Here is your data. This Priya takes note of the distance the car drives and the amount of time it takes to get to the destination for many different trips. So it looks like here we have 5, 10, 15 trips, so 15 points in your scatter plot. Why don't you go ahead and open Desmos, type in all this data, and create your scatter plot, calculate your line of best fit, and then find your correlation coefficient. And then we'll answer some questions. So when you're done with that process, this is what it should look like. We have all our data, our 15 data points. We have the equation y equals 0.93x plus 4.15. So it's an increasing line. You can see we have an R value of 0.9897, so close to 1. That means it's a really good model and it's a positive relationship between the two variables. Okay, let's answer a few questions. All right, here are the questions we want to go through about the data. You've already taken care of number 3 and you've already done number 5, but there is a follow-up question. Why don't you pause the video and go ahead and, using your Desmos results that we just saw, write down the answers to each of these problems, and then we will go over them. Go ahead and pause the video now. So here are your answers. Number 1, what are some of the other factors? Well, you could have traffic, stop signs, lights, and of course the speed limit. All right, which of these factors, including distance, most likely has the most consistent influence for all the car trips? And the answer is probably distance. The farther you go, the longer it would take. All right, number 3 we did. Number 4, what do the slope and y-intercept for the line of best fit mean in this situation? Well, the slope is 0.093, which means that is the number of minutes for each additional mile, per each additional mile driven. So just less than 1 minute for each extra mile. And the 4.15, your y-intercept, means that's the number of minutes to go 0 miles. So that's maybe getting in the car, turning on the car, setting the radio, that kind of stuff. So it's how many minutes for no miles. I'm sorry, that was number 4. Okay, number 5, it says, based on the value, how would you describe the strength of the linear relationship? Well, if you remember, it was very close to 1, so it is a strong, positive relationship. And number 6, how long do you think it would take Priya to make a trip of 90 miles if this linear relationship continues? So what we have here is we can use the model. I'll write it down again. Y equals 0.93x plus 4.15. And now we can plug in any number of distance, miles, in for x and calculate how long it should take based upon the model. And this should be a very good model because our R factor was so close to 1. So what I'm going to do is say y equals 0.93 times 90 miles plus 4.15, and we're going to end up with 87.85 minutes. So for 90 miles, it should take about 88 minutes. This next activity, called Correlation Zoo, what you want to do is for each situation, describe the relationship between the variables based upon the correlation coefficient. So you want to mention whether there's a strong relationship or a weak relationship and whether it's positive or negative. Why don't you go ahead and pause the video and try that now? All right, see how you did. So for each of the 6, I wrote down kind of what the best conclusion would be based upon those R values. So strong positive relationship, strong positive relationship. The 4th one down is a moderate strong positive relationship. So you might argue that anything greater than, the absolute value of R, so whether it's positive or negative, as long as it's greater than or equal to 0.8. So that means even if it's negative 0.85, it would be the absolute value of it is greater than 0.8. That is a strong relationship. If let's say it is greater than 0.5 but less than 0.8, that would be a moderate strong relationship. Don't let the absolute value throw you off there. It's just saying, regardless of whether it's positive or negative, as long as the magnitude of the value is bigger than 0.8 or much smaller than negative 0.8, it's strong. And likewise, moderate between 0.5 and 0.8, and it's really not a very good relationship or a weak relationship if it is less than 0.5. So this is weak or poor relationship. So you can use that kind of as a guide. It's not a hard and fast rule. It's just little guidelines to make some conclusions. All right, in this last example, you have a biologist trying to determine if a group of dolphins is a new species of dolphin or if it's is a new group of individuals within the same species of dolphin. The biologist measures the width of the largest part of the skull, zygomatic width, and the length in millimeters of the snout rostral length of 10 dolphins from the same group of individuals. And here's the data over here. So you got 10 data points. And when you put this in your graphing calculator or your Desmos, you'll get a line of best fit with this equation. So positive relationship and your y-intercept, and it has an R value of 0.201. So let's just think about that R value. That is not very strong. It's a positive relationship, but it is weak. So after checking the data, the biologist realizes that the first zygomatic width listed as 147 is an error. Right here, we have an error. It really should be 180. So what you want to do now is you want to go ahead and edit your data in Desmos and redo the calculation and find the new equation of the line of best fit and also the new correlation coefficient. Go ahead and do that now. Pause the video. Okay, so now you can see your new equation. You have positive relationship still, but note your R value is now closer to 1. So that one little change, right, for a very large rostal length, giving a much larger zygomatic length or width, has made this a much more strong model or moderately strong positive relationship. Okay, why do you think that the weak positive association became a moderately strong association? Well, it has to do with that one change was pretty dramatic. Now what you want to do is use technology to change the y value for both the first entry and the second entry in the table. So how does changing each point's y value impact the correlation coefficient? If we raise the second 147, we're going to see an even stronger or closer to 1 R value. And then it asks, can you change the two values to get the correlation coefficient closer to 1? The answer is yes. You want to go ahead and figure out how to go about doing that, trying different values. And then the last question, can you change the two values to get the relationship to change from a positive 1 to a negative 1? How could you take these two 147 values up here and make it so you now have a negative slope or a negative relationship, a negative R value? Why don't you go ahead and play with that? The more you play with the data, the better you'll get at understanding how the R value is impacted by the actual data values in the scatter plot. And that pretty much teaches you more about how to use the correlation coefficient to understand the fitness of that line of best fit. That concludes our lesson. Go ahead and try your homework assignment.